Hi, this is Mr. Beckstrom, and today I want to take a look at a problem from section 2.3. This is similar to problem number 14. This is looking at limits and also functions defined at a value a or a value x. They're looking at true or false statements. And we'll be taking a look at some of these to decide whether they're true or false, see if we can find any counterexamples, or if we believe that they're true for all cases. So let's take a look at this first one here. The first one says that the limit of, as x approaches a, of f of x is equal to L. So this means that as x approaches a, so since there's no little plus or minus, this means that from both sides, as x is approaching some limit, that means some y value from both sides. It has to be the same y value because it's saying that the limit exists. Then if we define f at a, then it's also equal to that same y value. So just looking at some of the examples that we've already done this section, we should know that that is not necessarily a true statement. And why? Because we've already looked at some graphs where that's not true. So let me use my pen here. So we might have something that looks like this, right? And we have a curve that comes up here, but right when it gets to that a value there, which we'll call that a, and we'll call that our limit value. Then it comes around like this, and let's say our actual a value is up here, and that's where our y value is. So taking a look at this, looking from the left, we're approaching this limit value here. Looking from the right, we're approaching that same limit value. So this is the y value where the limit exists because we're approaching that same y value from both sides. So we do say the limit exists right there because the point doesn't actually have to be there in order for the limit to exist. But if we actually look at f of a, that means the y value at this x value of a, notice it's way up here. And this y value and this y value are different, so this statement here would be false. So right away we can see that there is a counterexample right here, so something that looks like this. I can't quite think of another counterexample right off the top of my head. The only other thing you could probably say is if we got rid of that, and there doesn't even have to be an a there because the limit still exists here, and in this case f of a would be undefined because we don't even have an x value for a, and in this case it would still be false. So either one of these two situations are the two that come right off the top of my head. So definitely a false statement because we can find a couple of counterexamples there. So the next one here says the limit as x approaches a from the left, that's a little minus sign, of f of x is equal to L. Then the limit as x approaches a from the right of f of x is also equal to the same L, the same y value. And once again, we should know this is going to be a here. And we'll look at b over here. So think if we can think of a counterexample. Are there any that we've already looked at where we're from the left we're approaching one y value and from the right we're approaching another y value? And I mean, we can look at this graphically, we can look at this with equation wise. So you know, we can look at this. I mean, both of these we could write out as what type of equations? Yes, piecewise equations, right? And maybe we'll do one of those during this as well. But just graphically, we could think of it looking like this from the left and from the right, starting at that same x value, we go something like this. We put a little bit bigger of a dot there. All right. So from the left, we're approaching whatever this y value is there, y1, we'll call that. And from the right, we're approaching that y value right there. We'll call this y2. So from the right, this y value. From the left, we're approaching this y value. So definitely two different limits, depending on whether we're coming from the left or the right. So this is also a false statement because we can find a counterexample. Let's see if we can come up with a function, piecewise function, that would describe something like this. Let's say this x value here is 2, and we had something that f of x, some function that we set up as a piecewise function. I don't know if this is actually going to be right, but if x is, this one would be greater than or equal to 2, greater than or equal to 2, and then this one would be, oh, I've got to give myself some space to put those functions in. But if x is greater than or equal to 2, and if x is less than 2, so that describes this point, this x value, where these kind of split, and this looks like maybe it has like a y value there of -3, so maybe this is something like x squared minus 4, and maybe this is something like x squared plus 4 or something, plus 4. And then this way you can obviously see that these have two different limits, going from the left and going from the right. All right, let's take a look at C here. So C says if the limit as x approaches a of f of x is equal to L, and the limit of g of x as x approaches a is equal to L, or the limit as x approaches a of g of x is equal to L, you could say, then f of a is equal to g of a. So this is a little bit trickier than the first two. And here we kind of have to think about some of the quotients that we've looked at, some of the rational quotients. And here we can probably take a look at a couple of functions where we were able to remove one of the factors from the bottom. Let me kind of, so let's say we had something like the limit as x approaches, let's say we called it 3, and of f of x. All right, and let's say we said, and let's say we had something on the bottom like x squared minus 9, and that'll get rid of the x minus 3s. That's what we want to do, because that's going to end up getting a 0. And so on the top, we want to get x plus 3. So x plus 3. So if we actually solved that one here, when we plug the 3 in, notice that we're going to get a, oh, hold on just a moment here. That should have been a minus right there. Let me fix that. Notice if we plug the 3 in here, we're going to get a 0 over 0. But we can actually factor the bottom, cancel out the x minus 3s, and then we're going to end up getting a 1 over x plus 3. When we plug in the 3, that'll give us a 6. So this is actually 1 over 6, but if we look at f of 3 here, that's still going to be undefined, right? And then we can actually also find another limit as x approaches 3, and this one we'll just easily call it a 1 over x plus 3, and this one is also equal to 1 over 6. Sorry, I'm kind of messing around here. So both of these limits are the same value. They're both going to end up being 1 over 6 because we were able to kind of remove that x minus 3 out of both the top and the bottom here. But if we actually look at f of 3 for this first one here, if we plug that in, we're going to get a 0 over 0, and which is going to be undefined. And if we look at, so that's undefined because we have a 0 on the bottom, but if we look at the f of 3 over here, then that one is going to end up being a 1/6 because we plug that right in. So these are not equal. So in this case right here, or I'd probably call that a g of 3, excuse me. All right, I'm kind of messing around here. All right, the next one says the limit of f of x over g of x as x approaches a does not exist if g of a is equal to 0. Well, if we look at this right here, for kind of a very similar reason as C, we can also find a counterexample for this one, right? Because in this case right here, if we let this bottom function, the g of x here, equal 0, right? Because we plug that 3 in here, and 3 squared is 9, and 9 minus 9 is 0. We can still get an actual limit here that is defined, and the way we can get that is by getting that indeterminate form where we get the 0 over 0. We're able to cross out a factor from the top and the bottom that are the same, and then we can still find a limit there. So it would just be kind of using this first part of C that we did in order to show that, hey, if we get the indeterminate form where f of x and g of x are both equal to 0, and then we're able to factor something out of g of x and f of x, and then we end up getting a non-zero answer, then we're good. So that would be a counterexample to D there. And then for the last one here, it says E. Oops, I keep moving that around here. Let me move that back. All right, E. If the limit as x approaches 1 from the right of the square root of f of x is equal to the square root of x approaches 1 from the right of f of x, it follows that the limit as x approaches 1 of the square root of f of x is equal to the square root of the limit as x approaches 1 of f of x. All right, so let's think about that for just a minute. All right, and this one's a little bit tricky here, and what we have to do is we have to think about a case where the limit from the left and the limit from the right are not going to be the same when we're talking about a square root. And hopefully we've already seen a couple of these with the square roots, and that's going to occur when you're at 0 most of the time, right? When you have a 0 under that square root, because we can't even look at the square root of a negative number. So anytime we look at the limit under a square root, as long as it's something greater than 0, we can go from both sides of it. But once it gets down to 0, we're stuck because we can only go from the right of it. So what function can we put in here that when we plug a 1 in it, it's going to bring us down to 0? And that's going to actually be an x minus 1. So if we put an x minus 1 in here, then the limit, let me write that down here. Oh. All right, then the limit as x approaches 1 from the right of the square root of x plus 1 is equal to, well, that's going to be 0, right? Because we can look at it actually from the right-hand side. It's going to get closer and closer to 0. But we can't even evaluate that from the left-hand side. So it's not going to be true for as it approaches from both hand sides. So it can be true from the right. That doesn't necessarily mean it's going to be true from both hand sides. So that's a counterexample for this one. And it's probably the only one, or anything that's going to bring a function that's going to bring it down to 0. All right, if you have any questions, let me know. I know I kind of scribbled all over here, but hopefully you got some of the ideas that most of these, there's going to be a counterexample that we've looked at, and that's what they're trying to get you to do. All right, well, thank you, and have a great rest of the week.